Lesson 37, Reciprocal, Quotient, and Pythagorean Identities. Okay, so we're going to be getting into trigonometric identities, and to give you a feel for what we mean by this, I just want to bring up your guys' formula sheet. So let's look at the formula sheet here quick. So what we're getting into is this whole mess over here, right, on your formula sheet. You've probably been noticing that up until now and just kind of waiting for it to happen. Yeah, so when we say an identity, well, we've already been kind of dealing with some identities, haven't we? Because one identity would maybe be this one, that cotangent, right, is equal to 1 over tan theta, right? So this is like, it's an identity. So an identity is like, it also goes as this, right? Like, so this is what it is, but this is also what it is, right? So we call that an identity if it like goes by both things, okay? So like another example, like when we start getting into this, would be one like this, right? Sine squared theta plus cos squared theta is the same as just 1, right? So 1 is like another identity for sine squared theta and cos squared theta, okay? So that's what we mean. These are actually all going to be different identities that we're going to be going through. So now let's look at a few of these. So first off, some of the skills that we're going to learn, we're going to be proving identities. So what that means is we're going to be proving that one side of the equation is equal to the other side, which would mean that it was true for all values. So to prove something is going to be that it's always going to be true, right? No matter what. Okay. Now the other thing we're going to do is we're going to verify. So verifying things isn't going to mean that it's true for all values, because well, I'll show you what I mean. When we start like verifying, what we're going to do is we're going to put a number in and just make sure that it's the same for the left side and the right side. But that doesn't mean it's always the same, right? Because sometimes maybe it's just by chance that they're the same on both, like that's where the two graphs would cross or something like that, right? And it also wouldn't take into account maybe non-permissible values for one side and not the other. But I'll go through what I mean. Okay, so here are some good hints when we're solving different ways to do this. A lot of this unit is going to be like a puzzle where, you know, there's not one way to do it, but there's just kind of like easier and harder ways of doing it. So here's your hints. A lot of it won't make sense until we go through some, but one of them that we can look at is you want to start with the more complex side. If there are squares involved, then we're going to look for what's called the Pythagorean identity that I'll go through in a minute. One helpful one too is whenever you get something, let's say as like cosecant or something like that, we want to break it down into sine and cosine. It's just going to be easier to deal with. If you see you can factor, then you want to. This might allow you to cancel some things out. And then, yeah, we'll get into some examples like this. So this will be a good kind of a thing for you to look at after we've done some examples. I think it'll make more sense. So let's do a little review here first. So reciprocal identities, you guys have these, right? And these are on your formula sheet too, so you don't need to memorize them. And we've been dealing with this. So these are going to be things that we're on the lookout for, right? So we can change one thing into another thing to kind of play around with it. Quotient identities, well, you could just say that tan theta is the same thing as y over x or sine over cos. And then cotan is just flipped upside down, right? Just the other way around. All right, non-permissible values. So for our non-permissible values, just like in the other units, right, we can't divide by 0. Like we know this, right? Like in our rational expressions unit especially, we had something like x squared plus 2 over like x minus 1. And our non-permissible value here would be 1, right? Because that's what would make the bottom 0. We have to do the same with our trigonometric functions as well. So if I have a function like tan x or tan theta, either one, that's the same thing as sine x over cos x. Well, now we have to account for where is cos x equal to 0. Okay, so let's just actually do this one. Let's think about the unit circle for a second. So where is cos x equal to 0? So remember, cos is our like our x component, right? So it's like our x value there. So if we were at 0 degrees, our x value is 1. Right, so it's not there. It's not at 0 degrees, but it is at pi over 2, right? Because at pi over 2, x is 0 and y would be 1. Okay, And then it also happens again down here, right, at 3 pi over 2. So at 3 pi over 2, then x would be 0 and y would be -1. But either way, we can see that the non-permissible values for tan x, right, because we're dividing by cos x, would have to be at pi over 2 and then plus n pi, right? So adding n pi would get me 180 degrees around, and then doing it again, right? So that just for every one of those intervals all the way around. So we would say the non-permissible values for either tan or secant, yeah, just those two, have cos in the denominator, right? Because secant is just 1 over cos. So this would be your non-permissible values, right, for that one. And then similarly, cotangent and cosecant. So cotangent x is equal to cos x over sine x, right? Just flipped upside down. So now we're looking at where is sine x equal to 0? Okay, well that's like our y values now, right? So that would be at 0 degrees. And then it would also happen again over here at 180 or pi. So that would be -1 comma 0, right? So it's going to be where the angle is equal to n times pi, right? Because if it was, yeah, we've done a lot of those, so I think that'll make sense. So now just whenever we simplify things too, we just need to make sure we take into account our non-permissible values as well. Okay, so let's get into it. So given the equation cosecant theta is equal to cotan theta over cos theta, determine any non-permissible values of theta. So you might say, okay, I see it, cos theta, right? So you're like, okay, this definitely can't be equal to 0. And you'd be right on that, but you know what? We have to actually expand these things out a little bit too to get a better view of this. So here, I'm just going to write it one more time. So we've got cosecant theta is equal to cotan theta over cos theta. And now I'm going to expand everything out, right? So cosecant theta is the same thing as 1 over sine theta. And look what happened. We introduced sine theta in the denominator. So now that can't be 0 either. Okay? And I'll write this one out too. So we got cotan is equal to cos theta over sine theta. I'll put that in brackets just to remind me that that's that top one. Over, and then cos theta. Okay? And now if we look at all the places that we're dividing by 0 here, it's there, right? Well, it's in here too, right? We can't divide by 0 there, but we're already going to account for sine there. And then we can't divide by 0 here either. Okay, so let's account for those two situations. So, so sine theta cannot equal 0. So where would that happen? Well, that would happen at, so theta cannot equal 0, 180, or 360 degrees is what I'm doing these in. So what I'm doing there is I'm just getting a pattern, right? So I'm just going to write this out. And then let's write down what cos theta is not allowed to be. So that can't be, so theta then cannot equal 90 degrees, and it can't equal 270 degrees. Okay, so let's kind of put this together, right? So this is saying 0, like it can't be 0, can't be 90, can't be 180, can't be 270, and it can't be 360. So instead of like making two different, one for these non-permissible values and these non-permissible values, we can put this all together and just say, let's say that theta cannot equal, and then do you see how these are going up by 90? So that's what I'm going to do here. I'm going to go 90 degrees times n, where n is a member of the integers. Okay, that should account for all of it, right? It gets me to 0. If I multiply by 0, it gets me to 1, or 90 if I go by 1, and so on, right? It even gets me to the negative. I can go -90 if I go n is -1. Okay, and then just the other way of writing that with radians would be the same thing as, well, 90 degrees would be pi over 2 n, where n is a member of the integers. So either one of those if it was degrees or radians. All right, now prove the equation is an identity for all permissible values of theta. So now when I say prove, I want to make sure that the left side is equal to the right side. Okay, so that's the idea here. So let's write it out again. So we've got, actually, you know what? I'm gonna start from this point we were at here, right? Because we already did a bunch of the work. So it was 1 over sine theta is equal to, and then we had cos theta over sine theta over cos theta. Okay, and we call this the left side and that the right side, right? So I want to make sure that they're the same. Now you could, I could, like, you know, multiply this by something to see if I can get this one out, but that was step number one. It says try to deal with the more complicated one and see if we can reduce it to this one. It's usually easier to cancel things than it is to try to guess what I'd have to multiply by here to turn it into this. You guys have probably done this one already, so we just keep writing it down now. So 1 over sine theta is equal to, and then this would be the same thing as cos theta over sine theta, and then multiplying by the reciprocal. So this was like cos theta over 1, right? So we're going to flip that upside down. That's 1 over cos theta. So look at those cancel. And we do indeed end up with 1 over sine theta is equal to 1 over sine theta. So we've proven it. Because we'll say, you know, therefore the left side is equal to the right side. And that's what matters. All right, now verify the equation for an angle of pi over 3. So again, now what I'm going to do is I'm going to plug, you know, like pi over 3 into this side and into, well, the original equation, tell you the truth. I'll show you what I mean. And then we're going to see do those two numbers actually end up being the same. So here, so let's write out our equation again. So that would be cosecant theta is equal to cotan theta over cos theta. Okay, so now what we could do here, right? We could put pi over 3 in for the angle for each of these guys. But to tell you the truth, it was probably easier just to, like, because we were able to cancel there, right? So yeah, I think, you know, to make life easier here, we already canceled a bunch of these things. So yeah, let's just actually start from there. But you could, right? We actually could just put the angle in for all of these ones and make sure that the left is equal to the right. We'll do some of those in a bit here. So it'd be sine theta is equal to, yeah, so pi over 3, right? So 1 over pi over 3, right? I'm just kind of going back to here, is equal to, and then we already know that it's equal to, so this is almost kind of redundant, right? Because we definitely know that they're equal to each other, but let's figure out what these numbers are just for good practice. So this, right, 1 over sine pi over 3, well, what is that? So that would be the same thing as 1 over, and then let's figure out what the sine pi over 3 is. So sine at pi over 3 is really getting at this. So unit circle. So pi over 3, so right here, right? So up on this one. So sine of pi over 3 is asking for the y value at pi over 3, right? So it's really, so the answer to this is going to be root 3 over 2. Okay, so that's the one we're after. Okay, so that's going to be 1 over root 3 over 2, right? And then that's equal to 1 over root 3 over 2. And then just simplifying this out a bit, we can already see that they're equal to each other, right? And that should be fine. But let's actually write this out the way we should. So this would be the same thing as 2 over root 3. Nope, 2 over root 3. I just flipped it upside down, right? Just multiply by the reciprocal. Okay, and then technically we should rationalize the denominator as well. So multiply by root 3 on both. So this is the same thing as 2 root 3 over 3. And that's also the same on this side, 2 root 3 over 3. And if we would have put our numbers into here, right, and did it maybe, you know, from the cosecant place, we would have ended up getting the same thing, right? Okay, So that's the idea. So next one, simplify the expression tan theta cos theta over secant theta cotan theta. Okay, so one of the suggestions above, right on that first page, was saying that if we can, we'd like to break these things into cos in terms of cos and sine, right? So instead of it being tan, I'm going to rewrite this as sine theta over cos theta, and then rewrite the bottom as well. So let's just do the top. So to begin with, tan theta, that's the same thing as sine theta over cos theta, right? And then times cos theta. And then that was all over, right? I'm just around that line now. And then secant theta is the same thing as 1 over cos theta times, and then cotan theta was cos theta over sine theta. And then we can see that, you know, some magical things happen here. We've got cos theta and cos theta on the top. Those cancel. So all I'm left with in the numerator now is just sine theta. And then in the denominator, I've got cos theta and cos theta cancel, but be careful because it's still 1 over sine theta in the denominator. So let's rewrite this again just to make this look a bit more clear. This would now become sine theta, just in the numerator there by itself, over, and then we've still got 1 over sine theta. Okay, multiplying by the reciprocal there, that'd be the same thing as just sine theta times sine theta, which is the same thing as sine theta squared, or we like to write it as sine squared theta. All right, now Pythagorean identities. Okay, so what we're going to do now, they're called the Pythagorean identities because we can actually rewrite the Pythagorean theorem with our unit circle, right? So if you think about it, on our unit circle, if we had, you know, some length 1 right there, and then remember how the x component of this really was our cos theta, and the y component really was sine theta. Okay, so this is probably starting to make sense, right? So I can make an equation here now of sine squared theta plus cos squared theta, right? And that's also equal to 1, right? Because that'd be like 1 squared. Okay, so that's why that works, just the same reason as the Pythagorean theorem. So here is identity number 1. Now identity number 2 can come from just kind of playing around with this guy. So what if we divided everything by cos squared theta on this side? So if I divide this by cos squared theta, and this by cos squared theta, and this by cos squared theta, it was a weird theta, what do we get? Well, here we've got cos squared theta over cos squared theta, that's 1. And then here we've got sine squared theta over cos squared theta. Well, hey, wait a minute, that's tan squared theta. Okay, so that's this equation. We've got 1, right? That's this one. And then we've got tan squared theta. And then the last one, secant squared theta, well, that's the same thing as 1 over cos squared theta. Okay, so that's where we get this one from, just by dividing everything by cos squared theta. Now, the next one, I won't do it, but you get this one from dividing everything by sine squared theta. It ends up turning into this. So if you want to, give it a try. It ends up being the same. Okay, now these identities, when we're looking for them, they can take multiple forms, right? So maybe you'll see in the expression, you know, sine squared theta and cos squared theta. Then you'd be able to rewrite that thing as 1. So just for example, well, actually we don't have it there. Maybe I won't bring that up yet. Yeah, but if you see this, you can just rewrite it as 1. But maybe you see this in the expression, 1 minus cos squared theta. Okay, well, that's the same thing as just bringing the cos squared over to this side, right, and making it 1 minus. So it can go in many forms, and you have to be kind of on the lookout for all of them. Okay, so let's do some. Simplify the following. So, hey, 1 minus cos squared theta. Hey, we just did that. What is that the same as? What is an identity for this? Well, sine squared theta. So that means I can just take this guy and rewrite it. Okay, I actually just took a snippet and I snipped this part of your formula sheet too, just so we can kind of have them close to us, because these are the ones we're kind of focused on. So 1 minus cos squared theta, where are we getting that? Well, that's from this, right? It's up to you to make that connection, though, that that's the same thing as sine squared theta. Okay, so we'll do that. We'll replace the first one. So that's going to be the same thing as sine squared theta. And then the bottom, so again, I got something that looks suspicious, right? Okay, so now looking at the bottom here, we're going to do, so I'm looking at this secant squared theta, right? Well, so again, there's something fishy or something special happening here, right? I got a square going on, I got a -1. That really draws my attention over to this guy, doesn't it? Right? That looks similar, and I'm like, can I rearrange this? Can I put like a 1, like move this around a little bit? Well, yeah, what if I move the 1 over to that side, right? Made it a negative. So now tan squared theta is equal to secant squared theta minus 1. So this is all the same thing as just tan squared theta. Okay, and then all that's left to do is just to rewrite this in terms of either sine or cos. So I'm looking at this tan now. So this would be the same as sine squared theta over, and then tan squared theta would be the same thing as sine squared theta over cos squared theta. Put that in brackets so I can kind of get my bearings here. And then dividing by a fraction is the same as multiplying by the reciprocal, right? So that'd be the same now as sine squared theta times cos squared theta over sine squared theta. So those cancel. So that is all equal to cos squared theta. All right, next one. So now we've got sine squared theta plus sine squared theta times cotan squared theta. So, you know what? Let's see if we can make any use of this cotan squared theta, because I can't really figure out what that would be yet, right? Now you could do weird things, right? You could rewrite that cotan squared theta as like cosecant squared theta minus 1. But I think that's getting more confusing, not less confusing. So let's just try rewriting this in terms of sine or cos. So this is the same thing now as sine squared theta plus sine squared theta. And now rewriting this as, well, cotan squared theta is the same as cos squared theta over sine squared theta. Okay, and then hey, look at that. Sine squared theta, sine squared theta. Nice. This is all the same now as sine squared theta plus cos squared theta. All right, so that looks more simpler, but now that is this, isn't it? Right? So that's all equal to 1. So all of this was just, it boiled down to 1. Okay, let's do this one. Right, so yeah, I don't have any to the power of 4s, do I? Sine, there's nothing like that in my identities. One thing here I could imagine, though, is that maybe if I rewrite this instead of sines and coses, this would be like having x to the 4 minus y to the 4. So I've got a perfect square minus a perfect square. Maybe you see where I'm going with this. This is a difference of squares. Okay? So this would be the same thing. I'll write it with x and y so you can kind of get the gist here. This would be the same thing as x squared minus y squared times x squared plus y squared, right? Just standard difference of squares. So if we do this with sines and coses instead, this would be the same thing as sine squared theta minus, I'll do it the same as this one, minus cos squared theta, and then sine squared theta plus cos squared theta. Okay? Now, sine squared theta plus cos squared theta, hey, what's that? Well, that's the same thing as 1, isn't it? That's just our trig identity. Sine squared theta, cos squared theta. So that's just all equal to 1. So that's nice. It's like it canceled. And now we just have sine squared theta minus cos squared theta. Now that's probably as simple as we could get as just sine squared theta minus cos squared theta. But if you wanted to, this is actually a difference of squares again, isn't it? So we could write this one more time as sine theta minus cos theta times sine theta plus cos theta. But that's not really more simple, is it? So you'd probably just want to leave it like this. And I guess that kind of brings me to another point. This is a place in math where it kind of annoys students sometimes because they're trying to get the right answer. These are just identities, and when somebody says simplify this thing, sometimes that's a little subjective, like what's the simpler way to write something. So like I said, they're both right, they're both the same expression, but you know. All right, next one here. So hopefully we got enough room for this one. Write small if you can. Okay, this one looks like a mess, eh? A little bit on the confusing side. So what I recommend here is kind of dealing with the top to begin with. And again, this was one of our strategies here. Maybe I'll actually point you to it on the first page there. So one of our strategies was to write a sum or difference of fractions as a single fraction with a common denominator. So that's what we're going to do here. Sometimes it's useful to write this, right? The stuff I have circled there, all over a single denominator. So we need a common denominator there. So let's see if this makes sense. So here, let's write it out one more time. So we've got sine theta over cos theta plus cos theta over sine theta. And I'll just deal with this for now, and I'll just kind of forget about the bottom just for a second. Okay, so if I want to rewrite this over a common denominator, well, what would that be? Well, that would be, well, it could be, is just cos squared theta, or cos theta times sine theta, right? So what I'm going to do here is I'm going to multiply this side by cos theta, and so that's top and bottom. So cos theta, oh, that's not cos, on the top and bottom, right? So that's really just 1. And I'm going to multiply this side by sine theta on the top and bottom. Okay, do you kind of see that now? That if I do that, if I multiply these guys, then that's sine theta cos theta. And if I multiply these guys, that's sine theta cos theta. And then I just have to deal with the top. Okay, so just so you see it, I'm not going to do this every time, but this time I will. I'm going to write this now as sine theta, or sine squared theta, right? Sine theta times sine theta. And then over, I'm just going to write this as sine theta cos theta. Plus, and now this is cos squared theta over sine theta cos theta. Now, I wrote it out like 2 different terms again over the same denominator, so now we can just add those. But what we could have done in that last step, just since we know that that's going to be the case, is we could have wrote that all out as sine squared theta plus cos squared theta over, and then just over that single denominator of sine theta cos theta. Okay, does that make sense? Like hopefully you guys are good with that step, because I'm not going to do that middle step from now on. Okay, and then, you know, it's a little awkward now, but I should have been remembering that this was all over the whole time here. So I'm going to put brackets around that so I can kind of keep that as a piece. That's all over 1 over sine theta. Okay, now let's start to clean this mess up. So hey, look at what we got going on the top there. This on the top is, wasn't that 1 sine squared theta plus cos squared theta? Perfect. Okay, so this is really just 1 over, and then the bottom part here is sine theta cos theta. I can't really do anything with that, so I'm just going to write that again. So sine theta cos theta over, and here brackets again just to kind of keep my bearings here, 1 over sine theta. Okay, let's multiply by the reciprocal. I'll flip that thing upside down. So that's the same thing as 1 over sine theta cos theta times sine theta over 1. Right, just flipping that guy. So hey, look at that. Sine thetas cancel. So this is all the same as 1 over cos theta. And 1 over cos theta is the same thing as just secant theta. And there we go. Look at it. We went from that big mess down to just secant theta. All right. All right, last one. Prove the identity all of this, and then state the non-permissible values, and then verify for the value of x is equal to pi over 2. Okay, so let's prove this thing first. I'm just going to write it all down again over here. So this will be sine x, and then times cos squared x plus sine to the power of 3x is equal to 1 over cosecant x. All right. Okay, so now what we're going to do, remember one of the ones we want to look for is if we're able to factor anything. And if we see, I've got a sine in there, and I got 3 sines over here. So let's factor a sine out first. So I'm gonna write this as sine x, and then what I'd be left with, which would be cos squared x plus sine squared x. Hey, that's a good sign. Yeah, good sign. Okay, so then that would be equal to, and then cosecant x is really the same thing as 1, so this is 1 over sine x, or, you know, right off the bat, we could have seen that we have 1 over cosecant x. Well, that's just the same thing as sine x. Okay, now does that make sense? Well, yes, it does. So look at this. Cos squared x, sine squared x, those cancel, or not really cancel, that's 1. So that's just equal to 1. So in the end, yeah, we've got sine x is equal to sine x. So left side is in fact equal to the right side. Okay, so our NPVs, well, it's really coming from this, right? So 1 over cosecant x. So let's write that down for a second, like 1 over cosecant x. And if we think about it for a second, cosecant x is actually like, so cosecant x is equal to 1 over sine x, right? So it's not quite right to say that cosecant x, right? Cosecant x can't equal 0, because to tell you the truth, cosecant x would never equal 0, right? Because 1 divided by sine theta, there's nothing I can put in here that's ever going to get 0 out of that, right? So what I actually have to think about, and the better way to do this, is like I was saying before, we just want to rewrite this thing in terms of sine or cos, and then figure out where that can't equal 0, right? So this would be the same thing as 1 over sine x. And then there you go, I'm dividing by sine x. And so this makes sense to say sine x cannot equal 0, right? So that's really what I'm at. So anyway, that was probably a little bit confusing, but I just wanted to show you that it's not actually cosecant x that's not going to be the thing equal to 0. It's sine x. It's the thing that's like embedded in that. But okay, so now where is that going to happen? So sine x, that would be, so x cannot equal pi and then times n. Okay, so that'd be like at 0 degrees or pi, or 0 radians, and then pi, and then all the way around, right? Where n is a member of the integers. Okay, then last part here, we're going to just verify. So let's say if we had sine pi over 2 times cos squared pi over 2, put that in brackets so we know it belongs to that one, plus sine cubed pi over 2, and that's equal to, and you know what, instead of writing it as 1 over cosecant, it's going to be a lot easier just to think about that as being sine pi over 2. Okay, so now what we're thinking here is like the unit circle, really, right? So if I'm looking at this one, so what's the value of sine pi over 2? Well, that would be like 90 degrees, right? So what's my value, like my y value or my sine value at that point? That's equal to 1, okay? What is my, I know it's squared, but let's just think about for a second, what would just cos pi over 2 be? Well, that'd be 0, right? That'd be 90 degrees. That would be at 0, so it's like times 0 squared, but I don't really care about that. And then plus sine pi over 2, so that's going to be plus, well, sine of pi over 2 is 1, so like 1 to the power of 3. Okay, and that's equal to, and that's supposed to be equal to sine pi over 2 is 1. So does this work? Well, yes, this is all equal to 0. So 0 plus 1 is supposed to be equal to 1, and yes, 1 is in fact equal to 1. So we verified. So the left-hand side, or the left side, is equal to the right side. So again, just remember though that when we verified this, if you just verified it and we didn't prove it, then this wouldn't be proof that they were the same, that they were actually an identity, right?